Here we're starting chapter 6. New topic. But guys, is it really new? I mean, I guess it depends how you define new. But look, physics is physics is physics. Like at this point, you've now done, chapter 2, chapter 3. Forget about chapter 1. That's not physics. So you've done chapter 2, chapter 3, chapter 4, chapter 5. You guys are now, even if you don't realize it, you're in the physics groove, okay? The stuff we're going to be talking about in chapter 6, it is technically new stuff, but it's the same. It's the same feel, okay? All right, so chapter 6 is on momentum. Momentum has this symbol P, which every year kids are like, why is momentum P? And you know what I say to that? I say, why not? Why not P? And they say, well, shouldn't momentum be like M? That's mass. But then look, P, we just finished chapter 5. The last concept in chapter 5 was power. Wasn't power also P? Yeah, but here's the difference. There is a difference. Momentum is a lowercase p. Power is an upper capital P. But look, this is the first symbol where, like, what was F? Force. What was V? Velocities. Like all the letters kind of like, oh, V is velocity, F is force, A is acceleration. Now it's like P is momentum, huh? Well, look, what's the reason for that? English is not the only language in the world. I'm pretty sure P is from Latin, but whatever it is, you just got to know it. Is P power or is P momentum? It depends on the problem. All right. So the definition for momentum. Momentum is defined as mass times velocity. So let's start with the unit. What is mass measured in? Kilograms. What is velocity measured in? Meters per second. This is the unit for momentum. Now, let's take a trip down memory lane real quick. Force. What did we measure force in? The Newton. And what is a Newton? Kilogram meter over second squared. Okay, we just finished work and energy. What is work and energy measured in? Joule, which is kilogram meter squared over second squared. So look at how similar all of these are, right? And should you hardcore just memorize these or figure it out? Figure it out. Like, look at that. That's much better than just like randomly just, shoving it into some corner of your brain and not knowing why it's that way. Like, look, how could you figure out force? F equals MA. Boom. M is kilograms. A is meter per second squared. You can figure it out, right? Now, is there a shortcut unit for momentum? Like, what do I mean by shortcut unit? Well, for Newton, instead of writing all this, what do you write? N. For work and energy, instead of writing all that, you can just write joule. Is there a shortcut unit for momentum? There is not. However, in this class, and don't do this on the AP test, but look, in H44 at Peninsula High School, in this room, you have permission to use the Spaldo, okay? So you could be like, you could call that, since there's no name for it, I'm taking the name. There's no name for kilogram meter per second, so you have my permission to call it a Spaldo. Just don't do that on the AP test, though, because the grader might not be educated enough to know what a Spaldo is. So you're like, the block is moving with a momentum of 7 Spaldos. And I'll know what you mean. Yo.
Question, can we state that kilogram meter per second equals S?
You can, on my test, you can.
Like on the AP test, if you define it.
I wouldn't, because you know what? That's just a matter of the grader's ignorance. Okay? So the grader might not see that. In fact, you know what? Some people don't know who I am. Believe it or not, some people don't know. Okay? I'm kind of a big deal in this room because I'm the teacher, but outside this room, not so big a deal. Yeah. Yeah. Well, I'm always a big deal in my head.
You should go to the Nobel Prize in Physics to name kilogram meter per second the Spaldo.
One day, man. One day.
Do it.
Okay. Oh, Now, so momentum. Momentum, oops. Cancel that. Okay, momentum. Raise your hand if you've heard this word before today. Momentum. Okay, wow, that's like 4 of you who've never heard this. Okay, inertia. Raise your hand if you've heard that word. Bill Nye probably taught it to you, right? It's a property of matter. All right? Inertia. So momentum and inertia kind of, sound like the inertia of an object, the momentum of an object. They're very closely related, but they're different. Now, what is inertia? Inertia is the ability of an object to say, hell no, I'm not doing that. No. Not going to happen. What gives an object the ability to say, hell no? Mass. Mass is the only measure of inertia. Does inertia depend on velocity? No. What does inertia depend on? Mass. So for example, let's take a Honda Civic and a Toyota Sequoia, my big gas hog, my big old 10-mile, 9 miles to the gallon gas hog. Okay? My big old Toyota Sequoia and a Honda Civic. Which one has more inertia? The Sequoia. Because if you get behind the Sequoia, say parking brake is off, you put it in neutral, take the parking brake off, you get behind the Toyota Sequoia and you start to push it, you could probably get it to move, but what's the Sequoia going to be doing? Fighting you. It's going to be like, no. Now you get behind a Honda Civic, parking brake off, put it in neutral, you start pushing on a Honda Civic, and what's it going to say? Okay, all right. It's not going to fight you, dude. The Honda Civic's not going to fight you as much because it has less what? Mass. Inertia does not care about velocity. Now, momentum does. Is it possible for my Toyota Sequoia and a Honda Civic to have equal momentums? Yeah. Under what scenario? The Honda Civic is going fast. The Toyota Sequoia is going slow. Then you can have equal momentums. But will the inertias ever be equal? You know why? Because it's hard. It's harder to start a Sequoia, and it's harder to stop a Sequoia. Like once you have a Toyota Sequoia moving, it's going to be a lot harder to stop than a Honda Civic, right? So it works both ways. Starting motion and stopping motion, inertia works both ways. So you should really know inertia. I've seen this on the AP multiple choice probably 5 times on the multiple choice, where they want you to know what inertia is. Mass is it. Mass is the measure of inertia. Okay, next slide. Now, guys, I kind of lied to you. I lied. And I'm not ashamed to say it, because I did the right thing at the time. Now, so momentum basics. So here's our momentum equation. Momentum is mass times velocity. Now, back in chapter 4, I told you that Newton said, right, this is not my law, and I do have laws, okay? I haven't taught you any yet, but there are laws that I made up. And we'll talk about those after the AP, because they're still not on the AP exam, Spaldo's laws. Things like, well, never mind. F net equals MA. So whose law is that? Newton. That's Newton's second law. Newton never said this. He never, and that was my lie. I said, hey guys, here's Newton's second law. F net equals MA. Do you want to know what Newton said? Newton said this. And guess what? These are identical. They're 100% identical. What Newton said back in the day to his homies, what he said was, he's like, look, yo, the net force on an object will equal the change of momentum of the object divided by the time it takes to change the momentum. Now look, in this class, change of momentum is always going to be due, so let's see if you can guess. So here's momentum. If momentum changes, is it going to be due to the mass changing or the velocity changing? velocity. In this class, mass will stay constant, which is not always true in real life. If you're driving along and the person sitting next to you in the car in the passenger seat is annoying you, and you kick them out of your car, like as you're moving, just open the door, like push them out. Would the mass of your car change? Yeah. If you're driving along, like throwing stuff out, like littering, which I don't think is good to do, but the mass of your car would change, right? Or hey, look, you're driving your car. What's your car using? Gas. As your car uses gas, the mass goes down. But all that's going to be, that's not going to factor in here. In this class, mass will remain constant. Okay. So what will be our equation for change of momentum? Let's put it down here. So squeeze it right here. What will change of momentum be equal to? Mass times change in velocity, right? That would be change of momentum. So plug that in right here. Look what you get. So change of momentum is mass times change of velocity divided by time. Aha! What do you see? What is this right here? That's acceleration. I told you. Dude, what are we doing here? The exact same thing, but a different way. We're talking about the same exact stuff, force and time and mass. It's the same stuff, looking at it through a different lens. Does that make sense? Yeah. So, F net, Newton said, net force equals change of momentum over time. And guys, before you ever took physics, before you ever set foot in this room, you knew this equation. Instinctively, you knew it. Who remembers watching the water balloon toss out in the amphitheater? I was in it. Right? Do you guys remember the class competition? Yeah. The water balloon toss? Mm-hmm. Who were the final two teachers in there? Me and Greenberg. Who, by the way, if you don't know Greenberg, he teaches physics. Was it a coincidence that the final two competitors were physics teachers? I think not. I think it's because we what's that? So anyway, look, when you're doing a water balloon, I'm going to give you an example of this equation right here. If you're going to catch a water balloon that somebody threw at you from like 25 feet away, and the water balloon's flying through the air, right? It's coming at you. How do you catch the water balloon? Do you just let it slap your hands and don't move your arms? No, because the water balloon's going to break. You instinctively know to what? Cradle it. When the water balloon hits you, you cradle it. Now look, no matter what, you're going to have a change of momentum. No matter how you catch it, the water balloon is going to go from having a momentum to having no momentum because you're bringing it to rest, right? What will determine the force on that water balloon? The thing that will determine the force is what? How much time? Does it take a long time, a longer time, or a shorter time? If the time is shorter, what happens to the force? It's higher. If the time is longer, then that's a bigger denominator and the force is smaller, right? But either way, dude, the change of momentum, that's non-negotiable. That water balloon's coming at you, and you're going to take the water balloon from having a momentum to no momentum. Same thing for airbags in a car. If you're ever in a car accident, or if you have been in one, as awful as it is, I'll use this as an example here. You're in a car accident, what's the whole purpose of an airbag? An airbag pops out, and what does it do? I mean, dude, if you're in a car accident, there's no getting around this. You're going to have a change. Let me revert this. I'm making this messy. If you're in a car accident, you're going to have this. This is not negotiable. You're going to go from having a momentum to having no momentum, right? But what does the airbag do? The airbag makes the what? The time larger, which makes the force smaller, okay? Or Supreme Scream. Who's been on Supreme Scream before? That big tower, right? The big tower, and then they have they basically take you up the tower. I can't draw, but here's the idea. You're on the seat up here. They take you up the tower, and then what do? They drop you. Okay, so when they drop you, do they just let you smash into the ground? No, I mean, look, either way, dude, either way, you're going to have, when you reach, you're going to go faster, 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 right? So they have to stop you, right? You're going to have a change of momentum, but whether or not you walk away from that ride depends upon how slowly they change your momentum. If they just let you smash into the ground, what would be true for the time it takes to change the momentum? Very small. If you just go like this, if they just let you fall and you're like, bam, right? That's going to be an incredibly small time for your momentum change, which is going to give you a deadly force. It's going to kill you. So what do? You fall, and then right towards the bottom, what do? Slowly bring you to rest. They catch you and slowly bring you to rest. Okay? All right. Where are we here? All right, last page. Okay. Now, do you guys remember that video I showed you on making things faster? That video was a Friday, and I was like, whoa! When they got to the part when the guy was running on the treadmill, the college professor who was all about speed, they had this athlete running on a treadmill, and the treadmill was super duper fancy, and it could measure the force of the person's foot and the time of the step. So look, our graph for this chapter is force versus time. Now, there's one thing that's important, and that is the area under the graph. If you calculate this area, how are you doing it? You're going to go base, right? You take the base. What's the base here? Time. What's the height? Force. Well, we're looking at units, or we're looking at what's being plotted on the x and what's being plotted on the y. What do you get if you multiply time by force? Just look at your notes from like a minute ago, and let me write it a different way. Area equals force multiplied by time. What is that? That's the change of momentum. And yeah, some of you are like, Spaldo, hello, it's a triangle. Yeah, so you put a 1/2 in front, but you're still doing force multiplied by time. It's still force multiplied by time. Does that make sense? Area under a force time graph is change of momentum. All right. That's good for today. Any questions?